Welcome, Hornets, and thank you for joining me today. Today we're going to be taking a look at how do we graph polar functions, specifically cardioids, also types of Limacons. Now, there are three basic types of Limacons that we generally work with. They are the cardioid Limacons, where a divided by b equals 1, or when you're looking at the formula, you end up having r equals a plus a b cosine theta, or r equals a plus or minus, and I'm going to go plus or minus b sine of theta. Now, please be aware a and b are equal in this situation. Now, the graphs that I'm going to be working with are the graphs that I gave you the worksheet on, or gave a worksheet on. They look like this. I'm going to be taking a look first at the basic cardioids, and I'm going to work with 4 plus 4 cosine theta, and then r equals 2 minus cosine 2 cosine theta, r equals 3 plus 3 sine theta, and r equals 3 minus 3 sine theta. So let's go ahead and take a look at our first one. We're going to be taking a look at 4 plus 4 cosine of theta. Now, when you're doing this, please remember, I recommend you kind of get yourself into a rectangular looking graph. It is polar, so we could put the concentric circles in, but I'm not going to. I find that the concentric circles actually cause me a little bit of a problem, and unless I actually had graphing paper that had the polar graphing, I would rather avoid it. So let's go ahead and just take a look. And I'm going to start, now notice, if I start at 0 pi, so I'm going to start with theta equaling 0 pi, and I put 0 pi in, we know that the cosine of 0 pi is 1, and therefore 4 times 1 is 4, plus 4 makes 8. So all the way over here, I'm going to put an 8. So there's my first point. I'm also going to locate that I start at that value. This is so that we can get vector values all the way around. I'm now going to put in, what if I now have theta equals pi over 2? Well, if I have theta equals pi over 2, you'll notice that I'm going to get that 0 times 4 is 0 plus 4. And I'm now looking at, on theta equals pi over 2, half that distance. I'm going to put that right about here. Okay, once again, half the distance makes a right triangle. And then I'm going to go to pi. Theta equals pi. Now notice when I put in pi, I get negative 1. Negative 1 times 4 is negative 4, plus 4 makes 0, and I'm sitting on the pole. Then I'm going to continue with theta equals 3 pi over 2. This is also a 0, leaving me with 4 at this. Theta equals pi over 2. And then when I check for the last one, theta equals 2 pi. And I know that I'm approaching this infinitely. We're just going to go ahead and plot it as a point, and that would be where we end. So now when you're graphing these, keep in mind that you want to make sure that this bounces. See how I'm creating a lump there on both sides, and I want to try to make it as symmetric as I can. Now, as I go through, this is going to have to sweep up. Okay, it's going to keep going up, and then it's going to go ahead and come down. Now I'm going to try this again, because this tends to be kind of flat. Comes around, much better of a curve, curls over, and then comes down. This one is going to follow the same basic pattern. Try to make it a little flat. Comes around. And then comes around. Now, we want to make sure that when we're doing this, we are showing our movement. So we're going to be starting at the start, going around, curving around and bouncing. I like to show the bounce. Continues to curve and heads toward home. Okay? Now, if we're trying to find the tangent at 0, which is one of the things that we were asked when theta equals 0, we can see that that's going to be a vertical line. It's actually sitting on that polar axis so that theta equals pi over 2, and it's vertical. Okay. So how do we know that? Well, we can take our derivative and do our dy dx in the way we've discussed it in the past. This is once again theta equals pi sitting on the pole. And we can find our dy dx, whether it's vertical or horizontal, at the pole. Once again, until we actually get into our calculus and I give you the information, that's going to be a little bit harder for me to go through. So instead of giving you that, how about if we avoid that right now? And we'll have to do it in a different video. My goal today was simply trying to help you with the graphing, where a lot of people may have that difficulty. So the idea was more graphing than doing the calculus that goes with it, and we'll see that in a little bit. So here's our graph. Now I would like to plot points, so I am going to make sure that I put my 0 pi, r theta, so make sure I put my 8, 0 pi. You notice I just messed that up. Oh, hang on a minute, I'm going to press pause while I get the lights back on. All right, I'm back. Notice the lights are back on. I was able to discover something about how to work with the lights. Yay! Small things, right? And we're going to put our r theta right here. So we have two values where we start and stop, and we are starting at that point, 8, 0 pi. Now we can find other ones. For example, I could find out what pi over 4 is. I could find out what pi over 3 is, what pi over 2 is, and we would just find our exact values. This one right here, this is 4 pi over 2. This one is 0 pi. This one down here is 3 pi over 2. And then we continue back home to where we started. Alrighty, let's go ahead and do another one. This time, let's take a look at the next one on our sheet, which was r equals 2 minus 2 cosine theta. Notice that negative cosine theta is going to cause a reflection. So when we do this one, again, let me put it up here. We have r equals 2 minus 2 cosine of theta. Once again, you don't have to make this outrageous. Just get a graph. We often don't use the entire thing anyway. Here we go. So I'm now going to start by putting in 0. Now notice, when I put in 0 pi, I get 1, and 2 minus 2 is 0. So we're now starting on the pole. I'm going to put that I'm starting there. Once again, we had 0 pi, and that 0 pi gave me 0. Pi over 2 is going to give me 2. Pi. Notice when I put in pi, I get a negative. Negative 1 times 2 is 2, with the double negative makes it a plus. And I have 2 plus 2, which is giving me a length of 4. Then we go back to 3 pi over 2. 3 pi over 2 is going to be 2 again. And then 2 pi is back to 0 again. So I'm going to go ahead and I'm going to call this length 4. I want half of that going up. Once again, you should see that right triangle. These are the 2 points that are on that positive and negative theta pi over 2, and theta equals 3 pi over 2. I'm going to create that loop, do the mirrored image, kind of start flat, go up, Notice I'm going to go up beyond the point and then curl back down. Have it flat, curl above, and then have it come back down. Now, unless you plot a lot of points, you're not going to have it perfect. I'm now going to start with my vector movement. Curling around. Continuing. All the way through. And then finishing back here. Now I'm going to plot my points. I started at the point 0 pi, and my r was 0. So don't forget it's r theta. So we have 0, 0 pi, 2 pi over 2. This is now 4 pi, and then back to 2, 3 pi over 2, and then stop. Now keep in mind, we never actively reach 2 pi. We're going infinitely close, but we never want to start and stop at the same value. Otherwise, we have a problem as far as functions go. Let's take a look at r equaling 3 plus 3 sine theta. Alrighty, now notice as we set this up, here's our polar axis. Here's pi over 2, 3 pi over 2. Now if I start with 0, you'll notice I'm going to have a 3. So 0 pi leaves me with the sine of 0 pi is 0 times 3 is 0 plus 3 makes 3. Pi over 2 is going to give me 1 times 3 plus 3 makes 6. Pi. Once again, now we have 0. 0 times 3 is 0, plus 3 makes 3. 3 pi over 2. The sine of 3 pi over 2 is negative 1 times 3 plus 3 makes 0 again. Okay, so there we have a 0. And then we head back to our 2 pi, where we're going to have a 3 again. So let's now plot the points. 3, so if this is 3, over here is 6. So I'm going to make that little right triangle again. 3, go up the equal distance to make 6. Go down 3, make 6. Go over 3, make 6. Now, keep in mind that these are our concentric rings of this polar graph. We start here, and we're now going to go up to this point here. At pi, we're back to 3. Then we go to 0. So this is where we have our loop going up, our loop. Once again, we want to try and keep it equal or symmetric. Sometimes that's the hardest part, getting that curve to look like it's symmetric. Here we have our flat end, and that should be a little bit flat. That's forming almost a tangent line immediately. We start to swing past above that point, and then we're going to start connecting them. Once again, this is the hardest part. You're never going to be perfect unless you do more points. When you get to college, your teachers may ask you to do more points and get that graphing paper out so that you can graph the perfect Limacon. Now going to say, where do I start? I start here. I then move through my arc. I go around. I curl back through at pi. We then bounce at 3 pi over 2 and head back toward the start. We're going to plot our points. Our first point is 3, 0 pi. Then we have up here 6 pi over 2. We then continue with 3 pi. And then we go to 0, 3 pi over 2. And we finish at the 3, 2 pi. All right, let's do one more. This will be our last of these cardioids. And then we'll go ahead and take a look at our inner loop Limacons and our dimpled Limacons. So we have r minus equals 3 minus 3 sine theta. Notice the negative in front. That tells me that it's reflected through the axis, and I'm actually going to have one that's opening more downward. Once again, it'll be very apparent once we start plotting our points and identifying what's happening. Once again, I'm dealing with 3s and 6s, so I'm going to go over 3, make an equal amount, go over 6, equal amount, going up, and going up. This is where having the polar graphing paper will be more helpful, as we wouldn't have to guess. You'll notice they might be off a little bit. So now I'm going to plug in 0 pi. And we know 0 pi is going to give me a 0, and therefore I have the 3. Point is here. But notice when we hit pi over 2 and I get that 1, that's going to give me 3 minus 3, which is the 0. Notice we just created that loop. A little bit right there. It hits that 0. It then bounces toward 3 at pi. Now goes up. Now when I do my 3 pi over 2, and I get that negative for sine, notice that's going to give me a double negative and therefore 6. And when I go to 2 pi, I get another 0. 3 minus 0 is still 3. So we know we look like this. It's going to be flat at that end. We'll just kind of make it flat. And now try to curve it. Okay? Once again, this takes practice. I'm not very good at it, at least from my perspective. You might disagree. I tend to be a little bit more critical of myself. Notice that that's not good enough. I don't want to point. No cusps, please. These should be smooth and differentiable. If you do not make it smooth and differentiable, the AP board very well may mark you wrong. So cutting through and going up, and then curling back over. Once again, try to keep it as smooth as you can. We're starting here at 0 pi, so we're going to write start. I'm going to put oops, I had it upside down. So let's try and start at a different place, shall we? That was silly. Starting here, 0 pi, and therefore, let's start, and we have the point 3, 0 pi. Oh my, that took me a while. 0 pi over 2, 3 pi. This is now 6, 3 pi over 2, and we end at 2 pi equals 3 again. So I'm now going to do my vector form. So these are my little vector rays bouncing along, showing the movement that we wanted to show all the way around. Now the reason why we want that vector movement is because we're going to be integrating, and we're going to integrate along these values. If we know what we're looking at, we might be able to cut this in half and double our area, just like we did with even equations when we were working with our rectangular form. So this is graphing the cardioid limicons. You'll notice it's not very difficult, but it does take patience, and sometimes you might have to get rid of any cusps or any problems that you're looking at. Now, the next group of problems is called the dimpled limicon, and when you're looking at the dimpled limicon, you're now looking at the ratio of A over B is greater than 1. See, this was A divided by B equaled 1. This is A over B is greater than 1, as opposed to the inner loop, which is going to have A divided by B is less than 1. So let's take a look at one of these. R equals 4 plus 2 cosine theta. Well, we definitely have 4 divided by 2 is greater than 1. Let's just go ahead and set this up. And we're going to follow the exact same pattern that we did before. But notice this time, we're not going to get a 0, are we? Because these two aren't equal, when we put in pi, we're going to have a 2. So let's identify. 2, 4, 6. 2, 4, 6. We're going to have to go up 2, and then 4, and then down 2 and 4. And we might not be exactly right. Once again, if you have circles and you put the circles at the center or the pole and draw them through, you'll be able to get the concentric circles and perhaps be able to graph a little bit more accurately. I'm now going to plug in 0 pi. 0 pi gives me a 6. 2, 4, 6. I'm then going to have pi over 2 will give me a 4. Pi is giving me 2. Notice that's a negative cosine, or cosine of pi is negative 1 times 2. Negative 2 plus 4 makes 2. Okay, so we now have a point right here. We had 4 going up, 2, and 6. Then we have 3 pi over 2. This is going to give me, once again, 4. And we head back to 2 pi. And at 2 pi, we would end up having 6 again. So instead of having a dimple, okay, or the convex limicon, we're going to have it flat. It's going to cut through. And I want to get it as flat as I can. Okay, once again, a dimpled limicon is going to have that innie versus the outie. If I recall, this is between 1 and 2. And greater than 2 would give us that other. Now, I think I have my notes still here, and I can then show you what that would look like. Thank you for your patience. I went to go get this so that you could see what I was talking about. See, the dimpled limicon is between 1 and 2. The convex limicon is greater than 2 or equal to. Okay? And you notice that's that difference between the innie belly button and the outie belly button. Okay? So we're going to have just a little bit of a dimple going in. Doesn't have to be much. We're going back to 4 down here. Once again, just trying to make my curve as smooth as I can. Cuts through. Flat right there. Once again, it's going to swing outside so it's beyond that point and then curves back. Swings out, curves in, and we get our graph. We want to show the movement, so where do we start? And then cruising around. Please remember, we are going counterclockwise. That is the movements of our trig. We have this little bounce. Woo! Now remember, it is differentiable. So it is smooth. Keeps curling around. Unlike this, which has a cusp, this one has a very smooth bounce to it. And then comes back towards 0 again. We're now going to plot our points. We have 0, 6, 0 pi. We go to 4 pi over 2. We go to 2 at pi. And then we head back toward 4 at 3 pi over 2. And we finish at the start. And here we have our graph. Now, whether we're working with sine or cosine, it's all going to be the same. So let's go ahead and do a sine. This time I'm going to do a negative. So we're going to do r equals 3 minus 2 sine of theta. Again, I'm going to set it up. I'm only working with the ordinates. Those are these quadrantals. And when I look at this, you'll notice if I start at 0 pi, I get 3. And when we have at 3 pi over 2 with the negative, we'll have 5. So I'm going to break this up into 5 segments. 1, 2, 3, 4, 5. Going up, 1, 2, 3, 4, and 5. Going down, 1, 2, 3, 4, and 5. Going back, 1, 2, 3, 4, and 5. Now, they're not exact. This is where the circles would be helpful, at least if you wanted to be exact. Notice at 0 pi, I'm going to have 3 because I get a 0 for sine. But then I have a 1. When I subtract 2 from 3, I'm at 1. When I plug in pi, I get 0 again. When I put in 3 pi over 2, I'm all the way down here at 5. So we're going to make sure that we have this dimple occurring. Once again, it kind of gives us a little dip. Then curls back. This one's a harder one to graph sometimes. Don't worry too much. No one is perfect. We're just trying to get a good representation. We want the College Board to be able to see that we're trying. All right, that's the goal. Now, usually they will give us the picture, and as a result, we won't have to worry about graphing it. That's nice. And these are always on FRQs. They can give us what is the derivative. Those will be multiple choice at a point. So things that we calculate. All right, there's our picture. Putting where we start. Plotting our point. 3, 0 pi. 3 at pi. 5 at 3 pi over 2. And then finishing, and let's just put our 1 at pi over 2. Now I'm going to go ahead and put my movement. Starts there, goes through and kind of does its bump, and goes around and continues all the way until we reach the beginning again. And there we go. Those are the dimpled Limacons. All right. Let's go ahead and take a look then at an inner loop Limacon. Now be aware there are a couple of the, I believe they are the convex Limacons in the inner loop grouping. So just be aware, I'm only going to be working with some of the top ones. so that we can make sure that we get that less than 1 ratio between A and B. So if I have r of 2 plus 4 cosine theta, I can clearly see that A divided by B is 1/2, and that is less than 1. This is indeed an inner loop Limacon, and therefore we can expect that we're going to have a loop just like that. All right, here we go. Don't be afraid of it. Don't worry. You kind of have to have some faith in your ability to graph. It's okay. You guys have done a great job. You got through pre-calculus. You got through AP Calculus AB. If you're in pre-calculus, be aware you're going to have to know how to do this when you get to calculus, so you have no choice. Okay? When we're looking at the cosine of 0 pi, we're going to have 1 times 4 plus 2 makes 6. So I'm going to go ahead and I'm going to call this 2, 4, 6. 2, 4, 6. 2, 4, 6. 2, 4, 6. Starting at 6, right there. Pi over 2 gives me a 2. Boom. Notice 3 pi over 2 is also going to be a 2. But look what happens when we put in pi. We get -2. So 2 is here, and we are forced to reflect inside. That's what creates the inner loop. So we know we're supposed to be doing this on this piece, that on that piece, but inside this swings through and swings back. Flat at the end, extending beyond that point, and connecting these with a smooth curve. Swinging through, curving out, making sure it goes out. A little bit steep there, and then curving back. That's too flat. I'm just going to make it a little bit rounder. There we go. Now, when we plot the points, we started here. This happened to be our 6, 0 pi. We have a 2 at pi over 2. We had a 2 at 3 pi over 2. And therefore, we're looking at our -2 pi. And now I need my zeros. So we're asking ourselves, if 0 is on the pole, then that has to equal 2 plus 4 cosine theta. And you'll notice I end up with -2 divided by 4 equals cosine theta. And therefore I'm looking when cosine theta is equal to 1/2. This happens in the third and the fourth quadrant. After second and third quadrant, after pi over 2 and getting to pi, and then past pi over 2 in the third quadrant, heading toward 3 pi over 2. So in the second quadrant, and the third quadrant are what we're looking at. The reference angle is going to be pi over 3, so we're looking at 2 pi over 3 and 4 pi over 3 in the third quadrant. We're going to make sure that we list both of them, and we now have 0 at 2 pi over 3 and 0 at 4 pi over 3. Notice how I found those values? We go back to our trig, back to what we did in pre-calculus. Now the last thing I'm going to do is show my vector movement. Be careful because as I go through, I want to make sure I can clearly see it. Curls back and then through and back out. And we finish. There's an inner loop with a cosine. Let's take a look at an inner loop with a sine, shall we? Let's take a look at r equals -3 plus 6 sine theta. All righty. Setting up my graph. Going out in both directions, left and right, up and down. Now I'm going to start with 0 pi is going to give me a 0 for a -3. All right, well, let's just make sure we have 3, 6, 9. 3, 6, 9. 3 going up, 6, 9 going down, 3, 6, 9. So we just had a -3 at 0 pi, and that means I would be here reflected through the pole. I'm right there. Notice this is where I start this time. Now I'm going to go ahead and I'm going to put in pi over 2. Pi over 2 is a +3. See how I have -3 plus 6? It's +3. Wow, that forced us up. Then we're going to head to our next value, and that's going to give me, let's see, pi would be next. That's going to give me a -9, 0, -3. So at pi, we're now over here. Then when we put in 2 pi over 3, 2 pi over 3, 2 pi over 3, that's giving me -9. So here's +9. Reflected through is all the way up here. Notice that meant that we had 2 zeros right there, and we just went by it. We have this going up, going down. Oop, a little bit too flat there. Let's make it flat here. Curling around. Flat, curling around. And there we go. So we know that this point right here was at, let's see, 3 pi over 2. We had -3 at 0 pi. We had another -3 at pi. Notice these are backward. This up here was -9 at 3 pi over 2. We had 2 zeros. We have to find them. So 0 equals -3 plus 6 sine theta. Therefore, 1/2 is equal to sine theta. This is at pi over 6 and 5 pi over 6. So our first answer is going to be 0 at pi over 6. Notice that's between our 0 pi and pi over 2. Curls back into the second quadrant between pi over 2 and pi. And that's 0, 5 pi over 6. I'll put where I start, and I'm now going to show my vector. Goes like that, swings through, curls around, then curls back out, curls around, all the way up to where we had our 3 pi over 2, curls around, and then heads back to where we began again. And there we go. That is an inner loop for a sine. Now, when we're dealing with the convex, the only difference is instead of us having that dimple, it's actually going to kind of pop it out. We're going to have a curve. Please remember, it's differentiable, okay? And you're going to want to try that on your own. Now, in my next video, which I probably will have to make tomorrow, I'm going to go over the rose curves and show how we work with the rose curves for sine and cosine. And this will follow through with what we do in class tomorrow. As tomorrow, we're going to have to continue practicing this and making sure that we know what to do. All right, so for those of you who are hoping to see more of my videos, please be aware we will see the next one coming within a day or so. I hope that has helped. I hope this has kind of given you some insight for graphing those Limacons, specifically the dimpled cardioid and inner loop. If you have any questions, please make sure that you ask them, and I'll try to answer them as best I can. And if you like this, please remember to click like. For those of you in other classes, please consider going through this, and I hope you enjoyed it. I hope it made sense. This is another reason why you have to know your ratios and why you have to solve. Okay? Thank you very much. Take care and be well. Cheers, everybody. Bye-bye now.